Hi guys! Welcome back again to 𝗧𝗺𝗀 Tutorials. In this video, we're gonna solve another problem in thermodynamics and heat transfer in chapter 6, gas power cycle. So here is our example. An Otto cycle that is air standard has a compression ratio of 9.5. Air is at 100 kilopascal, 35 degrees Celsius, and 600 cubic centimeter. Before it undergoes isentropic process, 800 Kelvin is the temperature at the conclusion of the isentropic expansion process by utilizing particular heat values at room temperature. Determine A, the highest temperature and the pressure in the cycle. B, the amount of heat transfer in kilojoules. C, the thermal efficiency. And D, the mean effective pressure. So, the given in our problems are, we have the compression ratio is equal to V1 over V2 is equal to 9.5. We have pressure 1 is equal to 100 kilopascal. We have temperature 1. Temperature 1 is equal to 35 degrees Celsius. Let's convert it to Kelvin. Let us add 273 is equal to 308 Kelvin. So we have the temperature 4 is equal to 800 Kelvin. Our V1 is equal to 600 cubic centimeter. Our constant pressure is equal to 1.05 kilojoules per kilogram times Kelvin. Our constant volume is equal to 0.718 kilojoules over kilogram times Kelvin. For our gas constant, R is equal to 0.287 kilojoules per kilogram times Kelvin. For our specific capacities of air, K is equal to 1.4. So for the letter A, the highest temperature and pressure in the cycle, A is for the process 1 to 2, isentropic compression. So T2 is equal to T1 times V1 over V2, where V2 is also our compression ratio. I forgot the raise the power of K minus 1. So T2 is equal to the temperature 1, that is 308 Kelvin times 9.5 times 1. Raise to the power of 4 minus 1, that is equal to, our temperature 2 is equal to 757.9 Kelvin. So to solve the pressure 2, we use the ideal gas constant. P2 is equal to times V2 over T2 is equal to T pressure 3 pressure 1 times volume 1 is equal to temperature 1. Since we are looking for the pressure 2, so P2 is equal to V sub 1 times temperature 2 is all over volume 2 times the temperature 1. So volume V1 over V2 is also equal to our gas compression ratio. So I forgot the times V1. So since V1 volume 1 over volume 2, that is our compression ratio also. So 9.5 times our temperature 2, that is 757.9 Kelvin, all over the pressure temperature 1, 308 Kelvin, times our pressure 1, that is 100 kilopascal. Our pressure 2 is equal to 2,338 kilopascal. So for process 3 to 4, isentropic expansion. So isentropic expansion, T temperature 3 is equal to temperature 4 times the volume 4 all over the volume 3 raised to the power of K minus 1. So temperature 4 is equal to 800 Kelvin times 9.5 V sub 4 over V sub 3 is also our compression ratio. So 9.5 times raised to the power of 1.4 minus 1 is equal to 1,969 Kelvin. Next, for the process 2 to 3, V is equal to constant heat addition. So using the ideal gas equation, P sub 3 times V sub 3 over P3 is equal to P2 times V2 over P2. So we are looking for the pressure 3. So P3 is equal to temperature 3 over temperature 2 times the Kelvin. Pressure 2. Sorry. So let's plug in. So we have 1,969 Kelvin all over 757.9 Kelvin times the pressure 2, that is 3,338 kilopascal, that is equal to 672 kilopascal. So let's proceed to letter B. So using the PV is equal to MRT, we are looking for the mass. So mass is equal to pressure 1 times volume 1 is equal to our gas constant times the temperature 1. So that is equal to, so let's plug in 100 kilopascal times the volume 1, that is 0.00006 meter, a cubic meter, divided by our gas constant R, is equal to 0.287 kilopascal times cubic meter per kilogram times Kelvin times our temperature 1, that is 308 Kelvin. So cancel kilopascal, cubic meter, Kelvin. So our mass is equal to 6.788 times 10 raised to the power of -4 kilogram. So for our Q in is equal to mass times specific internal energy at state 3 minus specific internal energy at state 2 is equal also and mass times constant volume times temperature 3 minus temperature 2. So that is equal to our mass is 6.788 times 10 raised to the power of -4 kilogram times 0.718 kilojoules per kilogram times Kelvin times our temperature, that is temperature 3, that is 1969 minus temperature, that is 757.9 Kelvin, that is equal to 0.590 kilojoules. So kilogram, Kelvin, so our unit is kilojoules. For letter C, so our worknet process 421, V is equal to constant heat rejection. So our Q out is equal to mass times specific energy at state 4 minus specific internal energy at state 1 is equal to mass times constant volume times temperature 4 minus temperature 1, that is equal to -6.788 times 10 raised to the power of 4 kilogram times 0.78 kilojoules per kilogram times Kelvin times our temperature 4, that is 800 minus temperature 1, 308 Kelvin. So our Q out is equal to 0.240 kilojoules. Cancel kilogram, Kelvin cancel. So the remaining unit is kilojoules. So our work net is equal to Q in minus our Q out. So our Q in is equal to 0.590 minus 0.240 is equal to 0.350 kilojoules. So for our thermal efficiency, that is equal work net output all over the Q in is equal to, so our work net output is equal to 0.350 kilojoules over our work in is 0.590 kilojoules. Cancel the kilojoules, is equal to 59.4%. So our letter D is equal to volume minimum is equal to volume 2 is equal to V max over our R. So our MEP is equal to work net output over volume 1 minus volume 2, also equal to work net output is divided by V sub 1 times 1 minus 1 over R. So this is 0.350 kilojoules divided by our volume 1, that is 0.0006 cubic meter times 1 minus 1 over 9.5, and then let it convert to kilopascal. So kilopascal times cubic meter is equal to kilojoules. So our MEP is equal to 652 kilopascal. So this is our answer for letter D.